Good morning, everyone. I'd like to start by apologizing for taking such a long hiatus between postings. It was unintentional. I just kind of got caught up in a lot of family responsibilities, and my work-life balance has been a bit off lately, so I've sort of had to prioritize other things. And in the end, I think that I wasted a fair amount of time. Um, so I apologize for that. But let me start now trying to make up some of that lost ground. Okay, so it's a good thing that we're actually starting a brand new topic now, because it's been quite a while since I guess we've thought about any new material. So this is actually a good time to begin, a totally new topic. I'll remind you, though, that the last big unit that we had together was the unit on power series, and, functions defined by power series, which turn out to be analytic in the interior of the disk of convergence. And then you can differentiate them term by term and so on. So that was, a sort of self-contained unit. There were several videos on that, and it turned out to be quite involved piece of theory. But the good thing is that it's kind of a topic unto itself. It's not directly related to anything else. So it's a terribly useful topic, of course, because many, many functions of great importance in science and elsewhere are defined by power series. And so knowing their properties, knowing that they're analytic and they can be differentiated in a convenient way, term by term, is extremely important knowledge. All right, but now we're going to begin a totally new thing, which is, okay, the ultimate goal is to sort of reconstruct the Cauchy theory of integrals, complex integrals, in a more general form. That will allow us to dispense with the kinds of artificial restrictions on the region that we consider, which have always sort of been with us since the very beginning of the course. And let me tell you exactly what I mean by that. If you remember the last version of the KoshiGorsa Theorem, the last version of KoshiGorsa that we stated was version 4 in our numbering system. And what that basically said is that if f is analytic on a region, capital U, which is box convex with respect to one of its points, at least one. Let's say P, or P naught. So in other words, this region doesn't have to be box convex with respect to every one of its points. That would be a very, very strong restriction indeed. There are very few regions that have that property. Basically, axial boxes have that property, that they are box convex with respect to any of their points. Right, but there are very few regions that have that property. But that's too strong. But we just require this region U to be box convex with respect to one particular point, just one particular point in that region. So the paradigm example of this is an open disk. An open disk is box convex with respect to its center. Because if I take any second point in U, in that region, let's say U is an open disk, so just the interior of that circle. So if I take any second point, also in that same region, then the axial box with those two as opposite corners, including the boundary, right, is fully contained within U. Okay, now there are, of course, many other regions that are box convex with respect to a particular point, but it's still a very restrictive condition. For example, like an ellipse, the interior of an ellipse would be such a region. If I have a region which is the interior of some ellipse, that's also box convex with respect to its center. But there are still quite a small number of regions that have this property. We can't just take some arbitrary region. If I take some region, let's say that's shaped like a kidney bean, or a kidney, for that matter, right? Take some region like this. It's all this stuff. Okay, this would not apply. KoshiGorsa would not apply to this region, because there's no point with respect to which this is box convex. If you take any candidate point for P naught, you can always find some other point in U where the axial box with those two as opposite corners is not fully contained within U, because of these points here, right? Anyway, so yeah, there's a very small or limited number of regions that qualify. The rest of the theorem says the following. So F is analytic, right? And then gamma is a loop. Piecewise smooth. I'll remind you that in complex analysis, we always restrict attention to paths that are piecewise smooth. If we're going to integrate over some path, then it has to be piecewise smooth, just to make sure that the Riemann integral of a function over that path exists. Okay, so, but yeah, this gamma is not just a path. It's in particular a loop. Starts and ends at the same point. And it's a loop such that its trace is fully contained in that region. Okay, then the conclusion is that the integral of f around that loop is 0. We can write the integral this way as a loop integral. So that's the latest version of KoshiGorsa, just to recall a piece of theory that we talked about much earlier in the course. Okay, well, what we want to do, the goal now, is to sort of recapitulate this theory, reconstruct it, with the same conclusion, which is that integrating an analytic function around some sort of closed loop must give the answer 0. But we want to do it without this very artificial restriction to a region that happens to be box convex with respect to one of its points. Because, as I keep emphasizing, that's a highly specialized kind of condition on a region. It's a highly specialized type of shape that a region has to have to satisfy that condition. So an open disk satisfies it, which is great because open disks are very important. Open disks play a big role, sort of disproportionate role in the theory. But, there are some situations where you have a function that's analytic on a region that's not a disk. So, if you have such a situation where your region of analyticity has some sort of odd shape to it, it's not, let's say, an axial tile or an open disk or a half plane of one of the two axes or something like that. Even a half plane of some line doesn't count. If you think about it, if I choose like some line and look at one of its two half planes, this region here, that's not box convex with respect to any of its points, because you can consider things like this, where it goes outside. So yeah, even if your function happens to be analytic in such a simple region as a half plane, if the line is horizontal or vertical, then you're fine, because then one of its two half planes is box convex. You have to remember that these boxes have to be axial tiles. So this works okay, but this picture here does not. And that's just unacceptable. We want to be able to consider, let's say, a function that's analytic in a half plane, like an arbitrary half plane, or some other kind of region that is not necessarily either an axial tile or an open disk or an open elliptical region, or a half plane of a horizontal line or a half plane of a vertical line. There's just this very small list of basic shapes that work in the KoshiGorsa theory version 4. But it's just too small of a list to be really useful. And also, the other problem with it is that this condition of box convexity with respect to one point just is convenient because it makes the proofs work, but it has nothing to do with the phenomenon mathematically. This phenomenon here, where the integral of an analytic function vanishes, is sort of unrelated to that box convexity thing. It's just that the box convexity happens to be a convenient, sufficient condition. Convenient because it makes the proofs work out nicely. But it's not like the heart of the matter. See, the heart of the matter is really that the region U should not have any holes in it. So it's okay to have like a kidney bean shaped region, because a kidney bean shaped region has no holes in it. This region should be okay. When I say okay, what I mean is that there should still be a KoshiGorsa theorem for this. If I have some loop whose trace is fully inside here, then I should still be able to say that if I have a function f that's analytic in U, right? Let's say f is a function that's analytic exactly on U. And then the loop gamma, it happens to be a piecewise smooth loop in U, meaning that its trace is in U. Then I should still be able to reach the same conclusion. Can I still reach the same conclusion that this integral is 0? That's the question. And what I'm saying is it should be correct, because the region U is a fairly nice region. It's not an open disk, but again, it has no holes in it. That would be the problem, if the region has holes that the loop could wind around. So for example, let's say I have a region that's maybe has a very nice shape, like let's say it's an open disk with a closed disk removed from it. So we remove that closed disk, and everything that's left is my region U. So this closed disk here is part of U complement. Let me just call it capital V. And then the rest of U complement is stuff outside here. Let's call that W. So V union W is exactly the complement of U. By the complement, I just mean the whole complex plane minus the set U. So that has a very simple shape. Like it's basically made from two open disks by removing one from the other. But we don't expect the KoshiGorsa theorem to work for this region, because it's possible to have a loop that winds around that hole kind of non-trivially. And in that case, we don't really expect the KoshiGorsa theorem to be true. We can't expect it to be true because we've already seen a case where it's not true. We've seen the case of the punctured plane. Imagine like the plane punctured at the origin. Okay, and we know that if we integrate around a circle, certain analytic function on that region, namely 1 over z. The function 1 over z is certainly analytic on U, because the only point where it fails to be differentiable is at the origin, but the origin is not actually in U. And U is certainly a region. It's an open set because a singleton set is closed, and then the complement of a closed set is open. So U is certainly an open set. It's definitely connected, and it's obviously non-empty, so it does qualify as a region. And the function 1 over z is analytic on that region because it has a derivative everywhere. Its derivative is just minus 1 over z squared. And that always makes sense because z is not 0 on that region. Okay, so, but if we integrate that function 1 over z around that circle, we know that we get 1. If we integrate just like once counterclockwise. Sorry, we get 2 pi I. Okay, if we divide by 2 pi I, that gives us the winding number, which is 1. But the integral itself is 2 pi I. Not equal to 0 is the point. So, when you have a loop that winds around a hole in your region, then, although it's possible for the integral to come out to 0, we can't say that it's necessary that the integral comes out to 0, because there are cases where the integral does not come out to 0, such as this case here. Right, so what I'm saying is, it is possible to have a picture like this one here, in which the answer is 0. Like when you integrate some analytic function, let's say I have a function f that's analytic in the region U. So when you integrate f around this loop, it's possible that it could equal 0. This could happen, but it just doesn't have to happen. This is not necessarily 0. It might be 0 by chance, but it's not necessarily 0. There are cases where it's not, where it comes out to be a non-zero number, such as the case of this example here. Okay. So anyway, that's the point, is that if a region has a hole in it, then we have no expectation that the KoshiGorsa theorem should be true for that region. But if a region has no holes in it, such as this kidney bean-shaped region here, right, because it has no holes, it's reasonable to expect the KoshiGorsa theorem to still extend to this case, but we don't have the technology to prove that at the moment, because it's not box convex with respect to any one of its points. So our latest version of KoshiGorsa, version 4, does not apply. And so we're still sort of left in mystery as to whether the KoshiGorsa theorem is correct for this kidney bean-shaped region or not. And that's the kind of central question that this new investigation is going to be meant to answer. And this is going to yield version 5 of the KoshiGorsa, which will be the final version for us in our course. And it's called the homology version. It uses a brand new kind of machinery called homology, and we're going to get into what that means. Okay, but before I get into the meaning of homology, which, it takes a little bit of doing to set up, it takes a little bit of kind of fussy definitions to set up the theory of homology. But yeah, let's talk first about the notion of simple connectivity. Simple connectivity is the precise version of having no holes. When I say that a region has no holes, that's not a precise mathematical statement. It's just a kind of informal description on a visual basis. When you look at a region, when you look at a picture of it, you can generally tell just by intuition whether it has holes in it or not. We understand intuitively what that means. It's kind of like, you cut out a shape from a piece of paper, and if you punch some holes in it with a hole puncher, or something like that, you cut out a piece of it with a scissor, then we would say it has a hole in it. But what does that mean from a mathematical point of view? Hole punchers are not mathematical objects, right? Scissors are not mathematical objects. Paper is not a mathematical object. So we need a really rigorous definition of this concept, and that's what simple connectivity is. It's actually surprisingly simple to define, surprisingly easy to define. Okay, so we're going to let U, capital U, be a region in the complex plane. And I'll just remind you that region, the word region is a technical term as well, and it embraces 3 ideas. First of all, U has to be non-empty. Secondly, it has to be open. And thirdly, it has to be connected. Okay, remember that connected means that any 2 of its points can be joined by a continuous path that stays entirely in U. Okay, so let U be a region, right? We say that this region U is simply connected if for every point P in the complement of U, there is a continuous path. Now, okay, this is not the kind of path we're used to, so I really should probably give it a different name. I'm going to call it an unbounded path. And the idea is I'm still going to use the symbol gamma for this, just like I do for an ordinary path. But the idea is that instead of being defined on a closed interval, such as the closed interval 0 to 1, the time interval is going to be half-infinite interval, from time 0, including 0, all the way, covering all positive times. So it's an unbounded domain. Instead of a closed time interval, we have a half-infinite time interval. Okay, then the function itself is a continuous, or C0 function, going into the complex plane. Okay, such that gamma of 0, meaning the position, you can think of that as sort of motion of a particle. Think of the variable t as time, so we'll have gamma of t. T is going to begin at 0, so that's like the starting time, and the starting location is going to be the point P, which again is just some arbitrary point in the complement of U. Okay, and then as t increases from 0, let's say t starts to increase, then gamma of t can be thought of as kind of moving particle. The particle is tracing out some path or curve, but the time is allowed to extend all the way to infinity. So this point, a moving particle, can sort of meander around the plane. It doesn't have to stop. There's no stopping time. Okay, and what I want to have happen is that the range or trace of this path is fully contained in U complement. So it never touches the region U at all. And then the final thing is that gamma of time infinity, or plus infinity, is the point infinity in the complex, or in the extended complex plane. Obviously, infinity is not a point in the complex plane, but we can think of, yeah, we can define this extended complex number system, which usually is written as C with a line over it. And it's just basically the complex plane with one additional point, which we call infinity. The exact nature of that point is unimportant. Like, what is that point? Well, it doesn't matter. You can define it to be any object you like. Like, you can define it to be, let's say, the empty set if you like. It doesn't matter. The point is that we just name it, we give it its own name, infinity, and we add it to the set of complex numbers. And we also make a number of other definitions, such as the fact that z plus that object is always defined as that object. Right, so we can, in other words, extend the algebra of the complex number system slightly to encompass that new additional element. You think of it as like a point at infinity. Okay, so you can imagine, like, we have a plane, and then there's a kind of idealized point at infinity, infinitely far away, but just one. And that's called the extended complex number system. So if you want to, you could, make these formal definitions, but I'm not going to take that path. I'm not going to take that track. I'm going to not make any formal definitions at all. Instead, what I'm going to do is just use this expression here as a pure mnemonic device to stand for the following idea, that if I take gamma of t and I take its modulus, that is the distance to the origin, then the limit of that as t goes to plus infinity. Sorry, let me give myself a bit more room here. I'm going to let time t go to plus infinity. I'm going to look at the modulus of the moving point gamma of t, meaning its distance to the origin. And that limit is plus infinity in the sense that it gets arbitrarily large and positive. The modulus of gamma of t gets arbitrarily large and positive as t increases. So what that means is that the point gamma of t is wandering further and further away from the origin. Okay, now it doesn't have to do that in an increasing way. Let me draw you some pictures. Let's say here's gamma of 0, which is the point P. Okay, so the distance to the origin doesn't have to be strictly increasing. I mean, it can be. This point can wander along a curve to the point infinity. Whoops. And what I mean by that is that the point is moving with time. So let's say this is gamma of t1, gamma of t2, right? And those times are an increasing sequence of times. And then you see that the distance to the origin keeps getting bigger and bigger with no limit. It gets arbitrarily large. So these distances here grow arbitrarily large as t increases. All right, but it doesn't have to do that in a monotone fashion. Could look something like this. Let's say p is here, that's gamma of 0. But we could have a path that sort of does something like this, as long as it eventually wanders very far away. The distance to the origin doesn't have to be a monotone function, like monotonically increasing. It just has to tend to infinity in the long run. It has to get arbitrarily large and stay arbitrarily large as t grows. So that's what I mean by a path to infinity, a continuous path. By the way, this path I'm drawing here doesn't have to be smooth or even piecewise smooth. It can be very rough. It just has to be continuous. So this would also be an acceptable picture. Starting at p, let's say, you could have a very rough path that's like not differentiable anywhere, as long as it meanders away to infinity, meaning that the distance to the origin gets arbitrarily large and positive as t increases. That would also count. All right, so putting it all together, for every point p in the complement of u, there's a continuous unbounded path. So it's unbounded because it's going to infinity. This condition means that the path itself is like an unbounded function. Its modulus is not bounded. Its modulus gets arbitrarily large. And so really I should probably call it a path to infinity. Yeah, let me call it that. There's a continuous path to infinity. I'll put the word unbounded in parentheses. Okay, and so again, by path to infinity, or by this expression in scare quotes, what I really mean is this condition here. This is the technical condition. But then also notice that I'm also requiring the trace or range of that function to be entirely contained within u complement. So it never touches u. So yeah, let me draw you the picture, the complete picture of a simply connected region. It looks like this. Let's say here's my region u. And I just choose any point p in the complement of u. So not in u itself. Well, then I can find a path to infinity that totally avoids u. See? And the same is true for this point. I can find a path to... In fact, for a point like this, you can even just go take a straight line ray to infinity. Okay? You can see that in a lot of cases, a ray, just straight ray to infinity will suffice. But yeah, for every point of the complement, you can find some path to infinity. Now, you see, you could have a situation like this. this region is also simply connected. So let's say that's my region U, just everything shaded there. Okay, because, if you look at every point of the complement, like this point of the complement has a straight ray to infinity. So does this one. Okay, what about something like this? This point here, that's also a point of U complement. Okay, well, that doesn't have a straight ray to infinity, but it does have a path to infinity that totally avoids U. So does this point. Let me do that in some other color. I can take some path to infinity there. It completely avoids the region U. It stays fully within the complement. Now, to contrast that with the bad situation would be if you have a region that has a hole in it. This would not count. This would fail to satisfy the definition. See, this is a region. It is a region because it's a connected set. Notice, by the way, that simply connected, it presupposes connected, because the very definition of simply connected, going back here, requires U to be a region in the first place. U has to be a region in the first place. So that means I'm presupposing that it's connected. But connected is not the same as simply connected. I have to presuppose that it is connected, but even if it's connected, it doesn't have to be simply connected. See, this picture is an example where it is connected, because any 2 points in U can be joined by some path that stays in U. Okay, it's also open, because all the boundary points have been omitted, and it's also obviously non-empty, so it counts as a region. But I claim that it's not simply connected. All right, why not? What fails? Well, if you start looking at points of the complement, many of them do have a path to infinity, continuous path to infinity, that avoids the region. But there are certain points of the complement that don't. See, if you look at this point, that's in the complement of U. It's not actually in U itself. It sits within one of the holes. Okay? And if you try to take a path to infinity, you can't do it, because inevitably you're going to hit the region U itself. If you take any path from P to infinity, it's going to intersect the region U, which is, which violates the condition. To be simply connected, U has to have the property that, first of all, it's a region, and secondly, every point in its complement, every single point in its complement, has to be connected to infinity by some path that totally avoids U, doesn't intersect U at all. And this point here does not have that property. So that means that U is not simply connected. Okay. So you see, this captures the idea of having a hole, because what we mean by a hole, here's what we mean technically by a hole. A hole would just be some point in the complement, not actually in U itself, but in the complement of U, such that you can't, if you try to move away from that point, you can't do it without hitting U. Like, if I move away from that point via some continuous path, I'm eventually going to hit the region U again. If I move away from that point via some other path, I'm going to hit the region U again. If I move along this path, I'm going to hit the region again. That's true for every single path. You're eventually going to hit the region. So you see that there's a hole that point is sitting within, which is not actually part of the region itself. And every path is going to be blocked. Okay, these paths don't have to be like straight in any sense, but every single path away from that point P is going to be blocked eventually by the region itself. And so that's sort of exactly what we mean by a hole. There's a hole that P sits in. By a hole, here's what I mean. It's a region. Let's call it V. That would be this region here. So this is like a hole in U. Would be a region V that's a subset of U complement, such that for any point P in V, any path from P to infinity must intersect U somewhere. All right, and so a region that has a hole is not simply connected. If the region U has no holes, then it is simply connected, because having no holes means exactly that there's nowhere for such a point to sit. There's no region for that point to sit inside, so there can't be any such points. All points of the complement can therefore be connected to infinity without touching U. So an alternative way to state the definition, like an alternative rephrasing of the definition, is that a region, capital U, is said to be simply connected if and only if it has no holes. And by a hole, what I mean is this. This is the technical definition of that term. Okay, it just means, again, another region, V, which is fully inside the complement of U. doesn't overlap u at all. All right, such that, again, for any point in that region V, if you try to move away from that point toward infinity along any continuous path, so continuous path C0, right, then that path will intersect u. Okay? And if the region has no holes, then it's simply connected. Those are just equivalent rephrasings of that same definition. Okay, good. So that's what simple connectivity means as a technical matter. Okay, and now we're going to try to start constructing an acceptable theory of integration. We need a more general notion of integration to take advantage of this concept of simple connectivity, which is really kind of the heart of the matter. The existence of holes is the problem. The existence of holes is why KoshiGorsa might fail. And if there are no holes, if the region is simply connected, then KoshiGorsa should not fail. KoshiGorsa should be true. That's really the essence of KoshiGorsa. But unfortunately, to prove it, like the techniques of integration or the concept of integration that we've developed so far is not sufficient. We need a more sophisticated understanding of complex integration. So that requires sort of a tangent into some stuff that is going to look very abstract, but it's necessary. Okay, and so I'm going to start to introduce this technology or machinery of chains. And then certain types of chains in particular are called cycles. Okay, so you should think of it this way. A chain is going to be the thing corresponding to a path. It's like a path, but it's a more sophisticated notion. And then a cycle is going to be like a loop, which is a special type of path, but it's closed. It's closed on itself because it starts and ends at the same point. Right? So a chain is like a generalization of a path, and then a cycle is also a generalization of a loop. But chains and cycles have the same relationship to each other as paths and loops do to each other. Okay, but let me define what these things are. Now, this is going to be a little hard to come to grips with because it's a very new idea compared to anything you've seen before. All right, so the first thing I'm going to do is I'm going to define a set which I'm going to call script f of u. And these are going to be called, these are just formal sums of paths in U. Oh, here U is a region. It doesn't have to be simply connected, just an arbitrary region. Completely arbitrary region in the plane. So just fix that for the whole discussion. Okay, notice I'm not assuming that U is simply connected. So yeah, this set, script f of U, is going to consist of formal sums of paths in U. So let me also have a notation for the paths in U. Yeah, piecewise smooth, by the way. Because these have to be objects of integration. We have to be able to integrate over these. So I'll also introduce a notation like script p of u for just the set of all piecewise smooth paths, gamma, in the set u. And by that I just mean that the trace of that path is inside of u. That's what I mean by a path in a region, is that its trace is in the region. Trace is a subset of the region. Okay. So piecewise smooth paths that have a trace like inside that region, I'll call that script p of u. The P there stands for piecewise smooth path. Paths, I guess. Either one of those. Piecewise smooth or paths. But then I'm going to consider formal sums of paths. Now, I have to tell you what I mean by formal sums. Why the word formal? Okay. The reason for that is because what I'm not doing is adding paths, literally, as functions. So what I don't mean, let me first discuss what I don't mean, and then I'll discuss what I do mean. Okay, what I don't mean is that I have, let's say, two paths, gamma 1 and gamma 2, and those are both functions of time, let's say. And let me suppose that they have a common domain. Well, this goes into U, actually, because it's a path in U. And let's assume that these have a common domain. Let's say the interval from 0 to 1. Then I can literally add those two as functions, in the sense that its value at time t is gamma 1 of t plus gamma 2 of t. And this will define a new function, which we denote as the sum. And that's also a function from the same closed interval into... Well, actually, it's not necessarily into U, because, you see, just because this point is in U, and just because this point is in U, doesn't mean that their sum is in U. There are certain special sets that have that property, that they're closed under addition. Like the entire plane, for instance. If U happens to be the entire plane, then clearly the sum will still be in U, but it doesn't have to be in general. So the best that I can say is that it's a function into the complex plane. And that's like literal addition of paths. We can call this pointwise addition. Or a pointwise sum. That should remind you of something. We've already studied the concept of pointwise product. We talked about this in class a while ago. We talked about the idea of where you have two paths with the same time domain. And in the situation we encountered, it was like both paths avoided the origin. They both had the same time domain, which is the interval 0 to 1, and they both avoided the origin. Then you remember we defined this pointwise product, gamma 1 times gamma 2, whose value at t is by definition the product gamma 1 of t times gamma 2 of t for all t in this interval. And that product also avoids the origin, because the only way a product can be 0 is if one of the two factors can be 0. And then you remember we had this theorem that the winding number of the pointwise product with respect to the origin was just the sum of the two winding numbers individually, also with respect to the origin. We also proved that the pointwise quotient has a winding number with respect to the origin, which is the difference of the two individual winding numbers, also with respect to the origin. Okay, again, pointwise quotient means that its value at t is gamma 1 of t divided by gamma 2 of t. And again, that makes sense because gamma 2 of t is never 0. And this also avoids the origin, because gamma 1 is never 0. So the value of that fraction, avoids the origin. So this was like pointwise product and also pointwise quotient. But there's also a pointwise sum. It's the same basic definition. Instead of multiplying the two values, gamma 1 of t and gamma 2 of t, or instead of dividing those two values, you simply add the two values. This plus this. That forms the pointwise sum. So that's not what I mean by a formal sum. Instead, what I mean is that we essentially just have an expression in which we want to keep track of gamma 1 with like a coefficient of 1, and then we keep track of gamma 2 with another coefficient of 1, and we just put these into a list by putting a plus sign between them. It's a purely formal expression. It has no meaning other than that I'm mapping gamma 1 to a coefficient, and I'm mapping gamma 2 also to a coefficient, and both coefficients happen to be 1. But that mapping, instead of writing the mapping this way, where gamma 1 maps to the value 1, and gamma 2 maps to the value 1, instead of writing these two mapping arrows, I'm just using as an alternative notation. Just an alternative notation is I put the value 1 in brackets, and then write gamma 1 next to it, then write a plus sign, then put the other value 1 in brackets, and write gamma 2 next to it. Now that expression is being newly defined right now, and the meaning of it is exactly this. It's just really a function that maps gamma 1 to the value 1, and maps gamma 2 to the value 1 as well, and to complete the picture, it also maps every other path to 0 for all paths in U that are different from gamma 1 and gamma 2. So all the other paths, except for gamma 1 and gamma 2, are just sent to 0. And that means that if I were to write those terms, they would look like this, like there would be a 0 coefficient with some other thing, and then another 0 coefficient with some other thing. And you'd have uncountably many of those terms, because there's obviously an uncountable number of paths. The total number of paths in any region is uncountably infinite. So you'd have an infinite, or uncountably infinite number of terms, but all those terms are considered 0, because the coefficient is 0. So we just consider those terms to be 0, and we don't even write them. But anyway, this expression here is now being defined as simply a shorthand for this mapping. So what we really have is a function, a, let's call it, whose domain is all paths in U, all piecewise smooth paths. And what's the codomain? Well, it's the integers. And it takes gamma 1 and returns the value 1. It takes gamma 2 and returns the value 1. And then it takes every other value and returns, or every other path rather, and returns the value 0. For all paths gamma in U, which are not gamma 1 or gamma 2. So it's like an integer valued function. And notice that it's not just any old integer valued function on the set of paths. It has the special property that it maps all but finitely many paths to 0. It maps almost every path to 0. But there's a certain finite number of paths that are not mapped to 0. Namely, in this case, just gamma 1 and gamma 2 are not mapped to 0. But there's only a finite number of those. And then this is simply a name for that mapping. This is just an alternative name for the mapping A, because it's not very convenient to have to introduce a new letter every time we want a mapping like this. Sometimes it is convenient to give that mapping its own short name, like A. But sometimes it's more convenient to be able to just take all the information in the mapping A and represent it kind of as an abstract name for that function. See, this notation here is very nice because it takes all the information that's present in this mapping and just lays it all out for you, creating a new name for that mapping. So this is just alternative notation for A itself. And it shows you exactly what A does. It shows you that A maps gamma 1 to 1. It shows you that A maps gamma 2 to 1. And by default, A maps every other path to 0. So we can actually literally write equations like this. This would make sense because this is if gamma 3 is not gamma 1 or gamma 2. Because this thing here is just another name for A itself. And A will take gamma 3 and just map it to 0. So that's what formal sums are. They're really just these mappings. They're integer-valued mappings. Integer-valued function on the set of paths, piecewise smooth paths, which have the property that, again, all but finitely many paths map to 0. Okay, so that is what formal sums are by definition. So you see that this is a very precise definition. A formal sum is what? It's this. It's just any integer valued function on the set of paths that maps all but a finite number of those paths to 0. And you see, more generally, you can have a mapping like this. Let's say I have a function a, or let me call it something else, b, from the set of piecewise smooth paths in the region U into the integers, such that, let's say, gamma 1 is mapped to n1, some integer, gamma 2 is mapped to n2, and gamma k is mapped to n sub k, and then everything else is mapped to 0 by default. That's if gamma is like not any of the preceding ones. So B does all of this. Right? That would count as a formal sum. And how would we write that formal sum? We'd write it like this. You'd write it as a sum, and then you'd put the names of the paths, let's call them like gamma j, where j runs from 1 to k. And we're going to write the coefficients next to those. The corresponding values, in other words. I shouldn't really call them coefficients. They're only coefficients in a formal sense. They're coefficients in this formal expression. They're written as coefficients because they just stand right next to the gamma j. So in that sense, on a formal notational level, they're written as coefficients. But they're not really coefficients, they're values. Those are exactly the values of B. Okay, and so that would be the alternative notation for B. And that B belongs to the set of all formal sums over U. Formal sums of paths, that is. So that's the set F of U that I introduced is the set of all possible formal sums of paths that are in U. All the individual paths, gamma j's, are in U. Their traces are in U. But we can associate those paths with any integers we like, as long as there's only a finite number of those that are associated with non-zero integers. Okay, and another even more abstract way to write this would be to call the values, b of gamma, just like with any function. The way you write the value of the function is you write the name of the function and then you put the name of the input in parentheses right next to it. So that would be the value of the function. And then you can just write the gamma next to it. But we always put these coefficients in brackets. At least I do. Although in most books they don't bother doing that. Like in Alforce, which is the book that I'm using as a reference for preparing this material, Alforce doesn't bother writing the coefficients in brackets. So Alforce just literally writes this, like sum of nj gamma j. But I don't like that notation because, although, of course, if you're being very careful, the context should tell you what's meant. Right? Like if you're being very careful, you're reading the book very carefully, keeping in mind the distinction between pointwise sums and formal sums, then this expression shouldn't faze you because you're already kind of clued in and looking for that distinction. So the context would tell you that this is meant to be a formal sum rather than a pointwise sum. But since the notations are the same, this is also the way that a pointwise sum would be written. If all the gamma j's had the same domain, let's say all the gamma j's have the same time domain, all from like the closed interval 0 to 1, then you could also form like a literal pointwise sum, and the notation for it would be exactly the same notation. So the same notation would denote two totally different objects. Pointwise sum, which is itself a path, and then a formal sum, which is not a path. It's some mapping. Notice that these formal sums, these are not paths themselves. Definitely not a path. Rather, it's an integer-valued function on the set of paths. So totally different objects. Anyway, so to keep the notations distinct, my own innovation is to put brackets around the coefficients. So when you see an expression like this where all the coefficients are bracketed, specifically with square brackets, it's meant to indicate to you that this is meant to be a formal sum only, not a literal pointwise sum. So it's just a shorthand for this mapping. Anyway, so we can write it this way. And what are we summing over? Well, we're summing over all paths, actually. All paths in U. That's an uncountable number of terms. But you see, the vast, vast majority of those terms are 0. Because, provided we define. Okay, so I have to make a special definition. So by convention, if I put 0 in brackets and multiply it by a path, we're just going to consider that 0. That is the integer 0. We can think of it as an integer, or we can think of it as a real number, or as a complex number. It doesn't really matter. But we just define that to be 0. And so in these sums... Oh, okay, sorry. I really screwed that up. Let me take that back. Sorry, that was a mistake on my part. No, I don't mean defining it as 0, because it's actually not a number. When I write something like this, what does that really mean? It just means to indicate that gamma is mapped to 0. It's like a mapping. So what the convention really is that this mapping may be ignored, may be left unwritten in the formal sum. So anything that happens to be mapped to 0, any path, in other words, that happens to be mapped to 0, you don't need to write it in the formal sum. You can. Notice I'm saying may be left unwritten, but doesn't have to be left unwritten. So yeah, let me give you an example of that. Let's say I write something like this. 2 times gamma 1. Now I'm saying times, just for convenience. Like verbally, it's useful to be able to like say that. but it's not actually multiplication. This really just means that gamma 1 maps to the value 2, the integer 2. But when we write it as a formal sum, we do describe it that way, linguistically. As long as you understand what's really going on, it's fine to say that. So it's like 2 times gamma 1, then let's say we have negative 3 times gamma 2, then maybe we have 4 times gamma 3. Okay, and then I can also write something like 0 times gamma 4. That's a totally fine expression. And what it means is a mapping C in the set of all formal sums that has the following properties. Yeah, so C of gamma 1 would be 2, C of gamma 2 is negative 3, C of gamma 3 is 4, C of gamma 4 is 0, and then also C of gamma would be 0 for any gamma not equal to one of those. But you see that you can represent the same information by just writing this. In other words, you can just ignore this term. You just leave it unwritten. You don't have to leave it unwritten. You can include it if it's convenient to include it. But you can also just omit it. It doesn't change anything because you see, the way we interpret this notation, so I've already written the interpretation of the original, which is this, all this information here, right? Well, what's the information conveyed by this new symbol? Let me sort of ask it as a question. Is this also a legitimate symbol for C? C has this symbol. Just let me define C this way. And then I can ask, like, is it also legitimate to write the same C in this other form? And I'm going to show you that the answer is yes, just by representing the mapping information that this symbol carries. This symbol carries information about the mappings. What are the mappings? Okay, well, gamma 1, rather, is mapped to 2. Gamma 2 is mapped to negative 3. Gamma 3 is mapped to 4. And then every other gamma is mapped to 0, as long as gamma is not one of these first three. Okay, well, you see that those are the same exact mappings as are already written out over here, because gamma 4 fits into this case where it's not the same as, it's not gamma 1, gamma 2, or gamma 3. I'm assuming that, by the way, in this whole discussion, I'm assuming that, so let gamma 1, gamma 2, gamma 3, and gamma 4 be distinct, like in pairs, pairwise. Meaning no two of them are the same. No two of those are the same piecewise smooth path. All right, so gamma 4 is not gamma 1 or gamma 2 or gamma 3, and therefore it fits into this scheme. So gamma 4 does indeed map to 0. So that's consistent with this. Okay, and then any other gamma that's different from all 4 of them will still map to 0 according to this clause, and will also map to 0 according to this clause. So you see that they exactly match in their mappings, and therefore they represent the same function. So this is an alternative notation for C. The two notations carry the exact same information and therefore determine the exact same function from the set of piecewise set of piecewise smooth paths on U into the integers. The same exact function. So therefore it's acceptable to either include that term with a 0 coefficient or exclude it. Okay, so it's really more of a theorem than a convention. I suppose I really should call it that. So the term, a term with a 0 coefficient, can be included or can be omitted indifferently. It doesn't affect the actual value of that expression. Okay, so that expression will denote the same mapping either way, whether you include that term or not. So okay, that's really what I mean. I don't mean to say that it's equal to 0 because it's not actually a number. It's really just a symbol that's part of it's part of a notation. See, like this one term here is just a part of a larger symbol, and that symbol is just a name for some mapping. So I can't really say that it's equal to 0 or anything like that. But the point is that that small portion of this notation, this stretch of language right here, this stretch of symbols, can either be included in the notation or omitted from the notation, and it doesn't make any difference. That's really the theorem. Okay, so now this set of formal sums carries some sort of algebraic structure on it. It has what I'm going to call a limited algebraic structure. Okay, namely, there are two operations we can do that have natural definition. We can take two elements of it, let's call them A and B, and we can add them. It makes sense to add the two, and we get another element of that same set. Also, we can take some element of that set, A, and then some integer, let's call it M, and it makes sense to multiply by that integer. And I'm going to write that this way to be consistent with the previous notation. It's like a kind of scaling operation, but we write the scalar in parentheses. Also, the scalars are limited to integer-valued scalars only. And that's going to also be another formal sum. And let me define what these two operations are. So what are the two operations? Addition, but we have to define what we mean by addition, because these are brand new objects. These formal sums are certain mappings from the set of all paths into the integers. And we have to say what we mean by adding those objects. And then we also have to say what we mean by scaling one of those objects. Okay, so let me define, but basically the two operations are just like addition and scaling, except the scaling is limited to integer coefficients only, integer scalars. So it's not a full scaling operation. All right, anyway, the addition operation is defined in the following way. If I have A written as a formal sum like this, sorry, remember, we always should write the coefficients in brackets. I'm sort of violating my own convention. It's going to happen a lot. So there are no standard notations for these things. Different authors use different notations. So I'm trying to choose a middle ground, notationally, between being sort of very elegant but leaving room for misinterpretation, the way that Alforce does. So Alforce uses a very minimal notation. He uses like the minimum number of symbols necessary in every setting. But the problem with that is that then you have like ambiguous notations that you have to rely on the context to disambiguate them. And that can be tricky, especially for a beginner. So I'm trying to find a middle ground between that way of doing things versus something that would introduce brand new notations. Like some people would write this operation using a symbol that may be related to a plus sign but is different, like a circled plus. Or instead of using a sigma, they might use a big circled plus. Okay, I want to avoid that too because that just introduces a lot of new symbols that are very limited in their purpose. Okay, anyway, so I have this formal sum with these coefficients. And let's remember that the restriction is that all these coefficients are integers, and they're all 0 except finitely many. There's a certain finite collection of paths where you can have non-zero coefficients. But for all the rest of them, the coefficients are 0. Okay, and then let's say I have a second one. A second formal sum, that is. So the same things apply. Like every b of gamma is an integer, and b of gamma is 0 except for finitely many paths. Okay, so we can define their sum in the following way. I'm not going to write a colon because you'll see why in a minute. I'm just going to write the equation for it. We can define the sum in the following way. Just take the coefficient of gamma from A, take the coefficient of gamma from B, and add those as integers. That's just a sum of two integers, which is another integer. And you'll put that in brackets next to gamma, and then include every possible path. Now you see this qualifies as a formal sum because I'm still just using all the paths, all the piecewise smooth paths that are actually in the region U. Each one is being assigned an integer, namely this integer. And all but finitely many of those are 0. And here's how I know that. I know that A of gamma is 0 except when gamma is in some finite set. Let's say gamma 1 to gamma n. And I also know that B of gamma is 0 except when gamma is in some other finite set, which let me call, gamma 1 tilde to gamma m tilde. So there's some finite set of paths where the A coefficient may be non-zero, and there's some finite set of paths where the B coefficient may be non-zero. But what this means is that A of gamma plus B of gamma, which is the integer that appears here, right, as the coefficient of gamma, is going to equal 0 except when gamma is in the union of those two sets. And it may be 0 even when gamma is. Hold on, let me just write this down. See, okay, just to clarify, like, this sum may equal 0 even when gamma is in that set. Reason why that might happen is because, for example, let's say gamma happens to be gamma 1, and let's say it belongs to both sets, and let's say it's also like gamma tilde 1. So I'm assuming here that gamma 1, just for convenience, gamma 1 and gamma tilde 1 are the same, let's just say. So it's in both sets. Well, it might happen that A of gamma 1 and B of gamma 1 are negatives of each other. Like maybe this one is 3 and this one is negative 3. So when you add the two, you get 0, sort of incidentally. But the point is that if this word except is here, so I'm going to say that equivalently by saying that this is 0 whenever gamma is not in that set. That's really the key, is that if gamma is outside a certain finite set, notice, by the way, this is the union of two finite sets, so it's still a finite set. Right, the original set had n elements, and this other set had m elements, and this new set has n plus m elements. Okay, but anyway, so it's still a finite set, and when gamma is not in that set, then that means that A of gamma is definitely 0, because A of gamma is definitely 0 whenever gamma is not in this first set. And you see that if gamma is not in this union, then it certainly can't be in the first set. Does everyone follow that? If gamma is not in this union here, then certainly gamma is not any of those things, because those things are all in the union. So because gamma is not in that first set, then A of gamma will be 0 in that case. But similarly, if gamma is not in this union, then it also cannot be in this other set. So let me just change the phrasing here. Yeah, it can't be in this set either, because all of these elements belong to that union as well. So that means that b of gamma is also definitely 0. And if both terms are 0, then the sum is 0. So you see that we have a finite set consisting of n plus m specific paths in U, such that for any gamma not in that set, the coefficient is equal to 0. So you see that the coefficients are 0 for all but finitely many. For all paths except for finitely many paths. And that means that this is indeed a legitimate formal sum. So we get it by just adding the corresponding coefficients. Okay? And if both coefficients are 0, then we will get a 0 coefficient when you add them. But you can still get a 0 coefficient even when the original coefficients are non-zero if they happen to cancel each other out. And let's look at an example. This is a very simple example. Let's say I have 2 times gamma 1 plus negative 3 gamma 2. That's my A. And then my B is going to be, let's say, minus 4 gamma 2 plus 5 times gamma 3 plus negative 1 gamma 4. Okay, so how do I determine A plus B? Well, the answer is you just combine like terms. By definition, you combine like terms. So for example, the value of A at gamma 1 is 2. The value of B at gamma 1 is 0. And then you just put that as the coefficient of gamma 1. And so I'm going to just combine everything. So you see that this value is given to be 2, because that's the coefficient of gamma 1 in A. This value is 0, because that term doesn't appear. There's no gamma 1 term in B. So by the nature of this notation, it just means that B assigns the value 0 to gamma 1. Okay. Then there's gamma 2. I have to take A of gamma 2 plus B of gamma 2. Now it so happens that gamma 2 appears non-trivially. Oh, I'm sorry, the whole point of this is a very bad example, because the whole point of this was to show you the cancellations. So let me change this coefficient and make it a plus 3. Okay. So yeah, this coefficient is a minus 3, which you see here. That's the value that A assigns to gamma 2. But then also B assigns a value to gamma 2, which is plus 3. So you see that these just cancel out and give you a 0 coefficient overall. Just sort of by chance. Okay, now there's other terms as well. We also have to deal with gamma 3. And let's see what those are. Okay, this is 0 because that doesn't appear in A. This is 5. So the total coefficient here is 5. And then we have to deal with gamma 4. Okay, now I